Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, next up we have some more poster spotlights, and as always, I hope you find these very interesting and come ask them lots of questions tonight at their poster.
So I'm going to talk about NEXT, a system for real-world development, evaluation, and application of active learning. My name is Kevin Jameson. This is joint work with Lola Jane, Christopher Fernandez, Nick Gladdard, and Robert Nowak. So active learning is about data collection, and specifically I'm going to talk about data collection from human labelers. So the idea here is that we're going to find the same classifier, regression, or embedding, or ranking, but we're going to ask questions in an adaptive way, collect this data in an adaptive way, so we can get away with asking fewer questions in total, meaning fewer time and fewer money, or less money. But in practice, there's a lot of challenges to implement active learning in practice, either for empirical evaluations or for just in practice to exploit these sort of advantages. You need all this infrastructure. You need to recruit participants, but Mechanical Turk makes that kind of easy. But you need a GUI for participants to be answering questions. You need experimental dashboards. You need a database. But most importantly, you need this computational backend, because you're choosing these adaptive queries. So when you want to ask the next query, you have to do some computation to choose which query, or decide which query to ask next. And that's what NEXT takes care of. So NEXT is this computational real-time system that runs in the cloud and helps you so that all you have to worry about is coding up your algorithm, putting it up on the server, and then pointing it towards Mechanical Turk or whatever you want to do, and start answering questions. So it's really a system that makes active learning reproducible. So who uses NEXT? NEXT is used by ML researchers like myself. So for instance, the Air Force Research Lab uses NEXT to develop new active learning algorithms for image classification, for binary classification, and they run simultaneous studies to figure out which algorithms will actually work. Experimentalists use NEXT. So UW, University of Wisconsin psychologists use NEXT to find out what algorithms work best for their application. You run multiple algorithms at the same time. They're not coding up algorithms. They're just using algorithms that are already implemented for their application. And finally, NEXT is for practitioners. The New Yorker has this cartoon caption contest where they have a cartoon and they invite thousands of captions to be put in by their readers. And the idea here is they want to use active learning, state-of-the-art active learning techniques to find which is the caption that should win this contest at the end of the contest. And so they've been using NEXT. We've been working with them for the past several weeks, and we'll continue to work with them. And on every week, we collect hundreds of thousands of responses from thousands of people, and it really shows this sort of like real-world capability of NEXT for your applications. Thank you.
Hello, my name is Peter Vlag, and this is joint work with my postdoc Melis Kuhl. This work is relevant if you use precision recall and F-score to evaluate classifiers in situations where true negatives don't add value. If you've ever done some kind of experiment like that, chances are that you will have made one or two mistakes which will have biased your results. One common mistake is to use the arithmetic mean to average multiple F-scores, for instance, coming from cross-validation. This makes you overconfident about your model because you should use the harmonic mean instead, which is always lower than the arithmetic mean. There are several ways to mitigate this, but in this work we mitigate this by transforming all the quantities to linear scales relative to a baseline model, which is the always positive classifier. So the quantities are called precision gain, recall gain, and F-gain, and by doing this, you inherit all the advantages of ROC analysis. The second mistake that you might have made occurs when you use area under precision recall curve as a model selection criterion. So for instance, you might look at the middle panel here and conclude that the dashed line has higher area than the solid line, and therefore you would choose the dashed model. Actually, if you look at the precision recall gain curve on the right, it is the solid line which has higher area under the precision recall gain curve. And we prove formally that that means that your model has higher expected F-gain score in a very precise sense. Finally, you may want to switch from F1 score to F-beta score by using a weighted harmonic mean of your precision and recall. Current methods mean that if you switch to a different value of beta, you have to retune your decision threshold. Using the precision recall gain curves, we can derive a calibration procedure which gives you in one shot all optimal thresholds for any value of beta for the F-beta score. And if you want to know more details, come to my poster, which is poster number 25, which is towards the back of the poster room. Thank you.
Hi everyone, my name is Yann Dauphin, and I'm going to talk to you about this work on equilibrated adaptive learning rates for non-convex optimization. And this is joint work with Arm de Vries and Yoshua Bengio. So the key problem that we're tackling with this work is the question of whether we can make training deep neural networks easier in a principled way. And the approach that we're taking is using preconditioning. So in the two figures on the right, I illustrate what the idea is. So what can make optimization hard is when the contour lines around a minima or a critical point are uneven, so that you make progress slowly in certain directions. And preconditioning is a geometrical transformation where we make sure that the contour lines are as even as possible, so that you make fast progress in as many directions as possible. So in this paper, we present new theoretical and empirical evidence that the so-called equilibration preconditioner is comparatively better suited to non-convex problems when compared to what has been proposed before. And we show also that equilibration is related to RMS-prop, and that can help explain some of the success of RMS-prop for training deep networks. So equilibration methods are a family that was proposed by van der Sluis in 1969. And the simplest kind is row equilibration, where we scale the rows of a matrix by the norms, so the rows are equilibrated because now they have the same norm. Now we propose a new theoretical justification that is more general, where we show that this simple method is able to reduce an upper bound on the condition number. And we also give concrete theoretical justification for the use of equilibration in the non-convex setting. So finally, in terms of implementation, what's really nice, as you can see in the bottom right, the algorithm itself is very simple, and basically it's an upgrade on stochastic gradient descent. We also find experimentally that this method produces very good results and is comparable and better than RMS-prop in some of the settings that we've considered. If you want to learn more, we'd be happy to talk to you at poster 27. Thank you.
Hi, the title of our paper is Structured Transforms for Small Footprint Deep Learning. This is a joint work with Tara Sainath and Sanjeev Kumar. My name is Vikas Anwani. We are at Google Research, New York. So in this paper, we consider the problem of building compact deep learning pipelines that are suitable for deployment on mobile devices, wearable computers, mobile robotics. And there are a number of approaches available to build compact architectures, ranging from quantization of weights to imposing sparsity using L0 or L1 regularizers to low-rank assumption on parameter matrices, or sophisticated forms of weight sharing, of which convolution is a prime example. We propose a unified framework to learn structured parameter matrices and their generalizations. So structured matrices are matrices that can be characterized by much fewer than, they have much fewer degrees of freedom. So an n by n structured matrix that can be described in much fewer than n square parameters is a structured matrix, and examples include Topolov's, Vandermonde, Cauchy matrices that support fast linear algebra, fast matrix vector products, fast linear systems, solution to linear systems. So we tap into a previously ignored literature in numerical analysis on displacement operators that turn these structured matrices into low-rank matrices and give a very nice characterization of a broad family of structured matrices, which actually includes generating more general structured matrices by taking products of, let's say, Topolov's matrices or inverses and linear combinations and so on and so forth. So our approach leads to fast training procedures because of fast forward propagation, backward propagation, and it gives us a nice way to essentially span an entire continuum of parameter sharing schemes from highly structured to unstructured. We show in mobile speech and image classification problems dramatic acceleration in training time, as well as very strong compression relative to state-of-the-art models. So if you would like to learn more about this, please come and see us at poster number 34. Thank you.
Hi, I'm Oriol Vinyals, and I'm going to present the work we did with Meira Fortunato and Navdeep Jagli, named Pointer Networks. So last year, we presented at NIPS this sequence-to-sequence learning paradigm in which we showed that we could do machine translation by mapping from a sequence of French words to a sequence of English. So what we tried to answer in this work is whether we are kind of ready to try to tackle the following problem. Can we take the instance of a complicated problem such finding the traveling salesman problem, which is the path that goes through all the points, minimizing the length, and pose it in a supervised setting with the same framework that sequence-to-sequence proposes? So in this example, for example, I show the points, which would be the input set or sequence that the algorithm consumes, and the desired output, which is shown by supervised learning to the learning algorithm, would be just the set, basically the one that minimizes the length. We study a bunch of problems such as TSP, as I mentioned, or simpler ones like finding convex halls. And we tried a bunch of approaches, starting from sequence to sequence and going through attention models like the ones proposed by Montreal, called RNN search. But in the end, it turns out that the best approach is to actually think of this problem as the output instance should point to the input points rather than have a distribution over a fixed vocabulary. And that was very important to both achieve very good results on a limited set of tasks, algorithmic tasks, and also it was important to achieve generalization beyond the number of n, like the size of the problem that we trained on. So if you want to learn more about the architecture and what we tried and problems such underfitting, overfitting, and so on, we are at poster 22. And here you can see some examples of the mistakes that the neural network does on, for example, TSP. Thank you very much.
Okay, the second afternoon session was over, so please join me to thank all the speakers in the session.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.